This video is specifically for the linear programming. So let's start. Linear programming basically is used for optimization of our limited resource. There are a number of alternate solutions possible for the problem. And linear programming is basically a mathematical technique used to optimize your maximize or minimize our linear objective function. We'll see what is objective function, and also that is subject to set of linear constraint. That is also we'll see what is constraint. So here linear programming is a mathematical technique, and the term linear is used for the variable. So whatever variable we have, it will be linearly varying. It simply means that the relationship between our different variable can be represented in the form of straight line. Okay, let's move ahead and see what does it mean and what are the requirements for the linear programming. So in the linear programming, we have one objective function, and it is a main function which we need to optimize, and it should be clearly identifiable and measurable in a quantitative term like maximization of profit sales or minimization of cost. So if you have to, let's suppose you are in an industry and your objective is to maximize your profit or minimization of the cost based on constraint you have, then this is a mathematical technique that can help you to do objective function. Basically, do whether you have to quantify your maximization of profit, sales, or minimization of the cost. This is called as objective function. Then let's talk about constraint. What is constraint or condition? So these are the restrictions, basically or limited resource within which we need to optimize our objective function. So let's suppose you got objective function, and basically you need to maximize profit for one of the industry. Let's suppose you are making an iPhone or making a cell phone, and that your objective is to maximize the profit. Then what are the constraint you have? So constraint, let's suppose you will have constraint of manpower. Let's suppose you have constraint of machines. You have constraints of whatever the IC's requirement. Like, these are the constraint you have. So based on that constraint, you need to optimize your objective function. So constraints are nothing but these are the restrictions or limited resource within which we need to optimize our objective function, right? So based on our limited resource only, we have to optimize our objective function. And all the variable used in objective function and constraint should be linear and non-negative. That is one of the assumptions, or one of the reason that we are doing linear programming, that all the constraints are linear. It should be linear and non-negative. Linear, right? If I plot a graph, let's suppose if I plot a graph, and linearly if I plot a linear curve, it's basically if this is x, here's y. If x increases linearly, your y increases. So that's how your constraints looks like. Okay, so let's move ahead and understand the law and rule in linear programming. There are certain laws which needs to be followed in a linear programming. Start with law of certainty. In linear programming model, the various parameters like objective function, coefficient, constraint, resource are known exactly, and their value does not change with time. That is a law of certainty, that whatever resources we have, that are constant and it does not change with the time. That is a law of certainty we have, right? Second thing is law of proportionality. For example, if my 1 unit takes 3 hours to manufacture, my 2 unit will take 3 hours. This is again a law of proportionality which we have to follow while solving a problem in linear programming. Law of addition is basically, let's suppose my total cost is 4x plus 5y, then basically your x and y will directly get added to find a total cost. Basically, it will follow a law of addition. Similarly, there is a law of continuity. Basically, in LP, decision variable are continuous. That is, they are permitted to take any non-negative value that satisfy all constraint. So your decision variable is nothing but your x and y. These are nothing but your decision variable, and these are continuous basically, and they are non-negative terms. They will some value, and that should satisfy our constraint. So these are majorly the laws and the rule in linear programming that we have to follow. Okay, let's come at the general statement of linear programming. So, in linear programming, you will have one objective function. The objective function says that it is the objective that we need to fulfill, right? It could be maximize of objective function this, or it could be minimization. So this is the main objective function that we need to focus when we are working on LP. Okay, this is a function that maybe we need to maximize profit. Maybe let's suppose maximize z. It could be maximize profit, or it could be maximize sale, right? And objective function can be something minimization of the cost as well. That's again it based on the problem to problem. So we have to focus on objective function. This is the main thing that we need to find, and with objective function only you will get the final answer if you are talking about any optimum solution we are talking about. So with objective function, we will have such a set of constraint. So let's suppose that's what I told earlier, that if we have to manufacture something, if you're going to manufacture an cell phone, then your objective function should be in that case to maximize the profit. But what are the constraints you have? The constraint you have the limitation of the resources, the manpower, the machines, right? So these are the constraints that based on that constraint you need to optimize your objective function. So your constraints are in a linear form. So ax1, a2x2, a3x3 up to axn bn less than equal to b1, right? Similarly, a21x1, a22x2, a23x3 up less than b2. So these are the constraints we have. And my x1, x2, x3 are decision variable and are non-negative conditions. So these are non-negative. It should be greater than equal to 0. Okay, so whereas my aij, where this aij are nothing but my technological coefficient or substitution, and bi is nothing but our resource value. This we call it a resource value, and ci, this ci terms are called as a profit coefficient, and x1, x2, x3 are nothing but our decision or a choice variable. Okay, great. So what is the limitation of working on linear programming? The only limitation that it can work only up to two variable. It cannot go beyond two variable, because linear programming can be solved through graphically, and graphically we can have a limitation of up to two dimension, which is x and y. If you're having more than two variables, then we can choose alternate option, which is simplex method in a linear programming function. Okay, let's now focus on our linear programming function. What are the steps we have? So steps for graphical is, first you need to identify the problem. Define decision variable, objective function and constraint. So what does it mean? You need to define what are your decision variable, what is your objective function, and what is your constraint, right? Some equation and constraint. This you need to identify. Once you identify all this thing, then you need to draw the graph that include all the constraints. So based on this constraint, you need to draw a graph and identify a common feasible region, right? This is the second point, that you need to identify the common feasible region. Third is you need to find out the point within the region, feasible region, which optimize the objective function. And that point will give you my final solution. So if I tell you, first you need to identify your decision variable, what is x and what is y, what I need to optimize. Then you need to identify what is my objective function. Then you need to find the constraint. Okay, once you have all the constraint, then in that case you need to plot a graph with the value of constraint. Let's suppose there are three constraints and you plotted a graph, right? Something like this, something like this, and something like this. Then you need to find out my common feasible region, and then you need to find out the points, and those points you need to put in our z value or objective function to find the optimum point value. We will see by going through some of the numerical problems. So these are the steps. So now let's go to one of the problem. A company manufacture two products, A and B. A and B. Manufacturing and marketing data of the two products is given as below. First says the formulate the problem, and second say find the product that will have maximum profit. Okay, so now the product in the department having a welding of 2.5, and the capacity is having 1000. Okay. Similarly, for machining, you have 3, 1.5, and the capacity up to 1200. Similarly, if doing assembly, you have A is 1.5, B 4, and the capacity is 200. So these are three my constraints, and my profit is 120 for A, 100 for B, and this is nothing but my objective function. And we have two variables, x and y. So I have identified all the three things and I followed the first step as of now. Now I will write down my constraint, my first three constraint, and I will plot these three constraint in a graph, and I will identify my feasible region. So let's go ahead. So here, key decision is to determine my number of units produced for product A and B in a week. Let's suppose these are X and Y. Let's suppose these are X and Y are produced in a week. And feasible alternative are all the values. So basically X and Y should be greater than 0. And our objective function is to maximize the profit. Profit per unit is given as objective function, which is 120x plus 100y. So this is my objective function, which is I have identified already. Now I have a restriction of maximum time available for 3 departments, and the constraint are. So these are my time which is available, and this is my constraint. So 2x plus 2.5y doesn't equal to 1000. Right? This is for welding. This is my constraint. Let's suppose this is for welding. This is my constraint. Similarly, for machining, this is my constraint, and for assembly, this is my constraint. So simply I will plot this curve. So if I have to plot this curve, then what I need to understand is if I put x equal to 0 here, then I will get the y value, which is 400. Similarly, if I put if I put y equal to 0, I will get the value of x. Similarly, machining also I will get the 2 points. If x equal to 0, y equal to 800, and y equal to 0, then x equal to 400. Similarly, for this also I will get the 2 points. X equal to 0, y equal to 300, and y equal to 0, x equal to 800. From this, I will plot a graph. So for welding, I have made with the pink line, and if I see pink line, it will be drawn something like this. Okay, which is nothing but your 0 400, which is your 0 400, and second is 500 0 500 0. So I've joined the line. Okay, I'll just change the color back. Okay, then I will draw another line, and one thing to be noted, that if it's less than 0, which means our region should be less than below this line, means our concerned region will be in this direction. Our constraint is saying that our constraint should be less than or equal to this line which we have drawn. Similarly, if I look at the machining, I got 2 points, which is x equal to 0, y equal to 800. So 0, 800, and 400, 0. So for the machining, I have drawn here. This is my machining, right? Second line. And I have joined the second line. And similarly, I have drawn the third line, which is assembly, shown as red line. Now, and all three equations are less than equal to 0, which means our equation are defined less than equal to 0. Similarly, for the red line also is defined less than equal to 0, which means my final solution will be below this line. If it's greater than 0, if it's opposite line, if it's greater than 0, which means your line optimal solution is above and on the line, then direction will be opposite. Okay, so all the constraints are plotted on the graph to get a feasible region. Now my final optimum region or feasible region is denoted here as a shaded region, O, A, B, C, D. So this is my optimum solution region, right? And this is my feasible region, and at any point within the region can be our solution under the given constraint. So now I have point O, point A, point B, point C, and point D. So these are the 4 points I have, and I need to identify which point will give me my optimum solution. So to get the point B, I need to solve equation 3rd and equation 1st. And similarly, if I have to find out point C, then I need to solve equation 2 and equation 1. Okay, so now if we put the values of the corner point of feasible region in the objective function, the point which optimized the objective function gave my final optimum solution. Okay, so I have solved the equation basically to get the value of x and y. So x and y for one problem, for basically this is for corner point, this is for corner point B, and this is for corner point C. So if you solve these two equations, you will get the value of x and y. So now this is my optimum objective function. I will put value of x and y of this corner point. First, I have a, which is nothing but your 0 and 100, and I will get z a is 30,000. If I put b value with this value, I will get 53,000. For c value, I will get 49,000, and for d, I will get 48,000. And my objective was to maximize my profit. So my final answer will be, in that case, B, where I will having a maximum profit if I'm using x 235 and y 211.76. Okay. So one of the corner point of the feasible region gave the final solution because objective function is a straight line basically, and with the constant slope, as it moves away from the region, its value increases, and the optimum value will be one of the corner extreme point, and objective function will be tangent to that line to give a final optimum solution. So our objective function is nothing but a linear function or a straight line. As you move your objective function from this visible region, you will get the maximum point, and this is the B is the point where you will get your optimum solution. Okay, now let's understand what is binding constraint. So binding constraint is basically when we put the value of our optimum solution in the constraint. So let's suppose in our case, this is our x and y. If I put this value in my constraint means these are my constraint. Okay, if my constraints are satisfying or equal to RHS equal to LHS, if RHS equal to LHS, then it is a binding constraint, otherwise it is not binding. So when we put the value of optimum solution in the constraint, your LHS should be equal to your RHS. Then constraint is termed as binding, otherwise non-binding. And the final optimum solution is always obtained from binding constraint. So this is nothing but the binding constraint value, and this will give you whether your constraint is binding or non-binding. That is the whole objective. Now, if I proceed further, I can give you one more problem that can be solved here. So let's suppose there is one more problem that solves the LP problem for minimization. This problem is for the minimization. They have simply given the minimization of my objective function, which is 6x1 plus 4x2. And these are my three constraints. So to solve this constraint, basically I will get the points. If x1 is 0, x2 is 40 by 3, and x2 is 0, I will get x1 by 40 by 3. So first I got my 2 points. Okay. Similarly, for second equation 2, I got 2 points. x1 equal to 0, my x2 equals to 40, and similarly x2 equal to 0, then x1 40 by 3. Similarly, I got my third constraint points, and I will plot this point into the graph. So pink line I have drawn, it's 0, 40 by 3, and 45 by 3, 0. So pink line I have drawn, this is my equation 1, right? Okay. My second equation is the blue line, which is 0, 40, and 40 by 3, 0, which is denoted by a blue line. So 0, 40 is this point and connected with this point, right? And also the one thing you notice that it is greater than 0, which means your line should be your optimum region, feasible region should be above than this curve. That greater than is basically saying above or on the line. So basically my pink line, if I show, it will be forming like this. This is my optimum solution because it's saying on the line or above the line. So this is my region. Similarly, for blue curve, the blue line will be similarly forming something like this, right? And I have one more equation, which is third as denoted by green. So this also will be greater than 0. Here it is greater than 0. So it should be going on or above the line. So if I find out my feasible region, it will be something like this. This will be my feasible region, right? And the points which I have, one point this, A, B, and C. These are my 3 corner points. Okay, so A point I already know, C point I already know, B point I can find out by solving blue and green line. And blue and green line are nothing but your this 2 equation. Then we'll get a B point. So by solving these 2 point, I will get my 12, 4. And this value I will put in my optimum objective function, which is nothing but 6x1 plus 4x2. Now I have 3 points. One is A, which is 0, 40. My ZA comes 160. And for B point, it is 12, 4. ZB comes 88. And for C point, ZC comes 132. And my objective is to find the minimization. So for minimization, 88 is your answer. Okay. So this is the problem for solving minimization problem. Okay. Let's understand one more thing regarding the redundant, degenerate, unnecessary constraint. So if you see clearly in this diagram, this pink curve is not playing any role in my final optimum solution, right? This pink curve is basically away from all my feasible region, right? The pink curve. If this pink curve is here or it is not there, it has nothing to do with my optimum solution, right? So this is nothing but an unnecessary constraint, or it's a redundant constraint which is there. The constraint which does not become a part of my boundary making feasible region is termed as redundant constraint. So this is my redundant constraint. Second thing, thus inclusion and exclusion of such constraint does not affect my final optimum solution of the problem. Either the pink line should be there, pink line means the first equation. Either this equation is there or not there, it has nothing to do with my final optimum solution because it's not being part of my optimum solution. Okay, great. Now let's go through some of the special cases of my linear programming. My first case is infinite or multi-optimum solution. So imagine that you are calculating the z value at A, z value at B, and z value at C, and all are coming same, right? Let's suppose coming at 80, 80, 80. Then you will see that you have infinite multi-optimum solution. When can be happen? What is the possibility? This can be possible when the slope of objective function 4x plus 6y, right? If the slope of my objective function become equal to my constraint, right? If it like 2x plus 3y, then let's suppose this is less than equal to 100, then this will give following a same slope line and will give multi-optimum values. So infinite number of solutions means we get the same optimum value of objective function for different varying variable. You have different variables, different x and y, but you are getting the same z value. That is a case of infinite solution. We always get the unique solution when the slope of objective function is different from my constraint. If my slope of objective function and constraint is different, you will get a unique solution. But if the slope is same, then you will get the infinite solution. Infinite number of solutions is obtained when the slope of objective function become equal to one of the binding constraint. So that is how you will get the infinite multi-optimum solution. Let's go to another case, which is no solution and infeasibility. So in that case, in some condition or constraint, some constraints are inconsistent in such a manner that it is not possible to find a feasible region, and where all the constraints are satisfied, it is termed as no solution. So let's suppose you have one curve which is having this region, and again you have one more curve which is pointing out outward dash. There is no common region in that region, so you will find a no solution for this equation, and it called as no solution or infeasibility. Okay, let's move ahead looking at unbounded solution. So in some condition, the highest value of objective function goes to up to infinite, right? There could be possibility. It simply means that the common feasible region is not bounded by the limit on the constraint. So the constraint is not bounded by another constraint, and it is simply termed as unbounded solution. For example, I have made one example. So if I have to maximize x plus y, and I have constraint 1 x minus y greater than equal to 0 and xy greater than equal to 0. So if I have to plot this, so I have drawn this curve, and you have one x greater than 0 and y greater than 0, right? So my final objective function, final constraint will be in this direction, right? So in this direction, you have infinite points which can be used to find the value of constraint, right? So I'll just shade again x minus y greater than 2, then you have this curve drawn, then you have another constraint x and y greater than 0, then y greater than 0, x greater than 0, then this is my point of region. And this is unbounded, right? It can be infinite. It can be infinite. So this is called as unbounded solution. So these are the basics of linear programming. I hope you like the video. If you have any topic related to any subject in mechanical engineering, you can comment down. I will try to make a video on that. I will make another video on Simplex. So I would need your support. Thank you all.